Today I'm continuing my papers on onion theory with a discussion of the tau meson, the D mesons, and other Kaonium mesons. And in onion theory, when you have two kaons in orbit, you can call it Kaonium. And so that's what I'm discussing here is mesons that have two kaons in orbit. And there are two basic types of kaon, which is one of the keys to understanding the onion theory model and how it's superior to the quark model. Because in current theory, they don't recognize the lower energy type. And basically, we have the two basic types that I discussed in my video on kaons. And you have, say, a muon and a pion in orbit, which is a K-long, or two pions forming a K-short. And then you can have an electron in the middle forming a charged kaon. But you can also have a lower energy state where only one of the pions is relativistic. In this case, you can think of it as one stationary pion being orbited by a relativistic pion. And because of that, the total mass energy is reduced by 100 or 105 MeV per c squared. According to the model, it would be 105, but in real-world scenarios, it seems to be closer to 100 for reasons that need to be determined. But I call that reduced energy kaon the KD, or for de-excited kaon. And it does not appear to appear by itself, because we haven't observed it, but it does appear within other more complicated resonances. So the mass energies are known: the K0 497.614, the charge kaon 493.677, and the KD has an energy of about 397.47 in the K star 892 that I'll discuss. Because it doesn't have a free mass, I just picked one that seemed to be in the middle of the range. It seems to vary from about 392 to 402 in different resonances. But we need to be able to sort out the effects of the resonances, because they may have magnetic coupling that increases the mass. It's totally independent of what's going on with the KD resonance. So anyway, we can have different types of kaonium. We can have a KD and a KD, a KD and a K, and two regular kaons. And then we can have different types of relativistic mass energy. If they're co-located or nested orbits, it'll have zero additional mass, in which you just essentially sum the masses of the two kaons. Or it can have 35 MeV per c squared per particle, or 70 MeV per c squared per particle. Now the base ones, where we have no additional energy because their orbits are co-located or nested, are the omega, which has a mass of 782, and we have the K star 892s, which has both neutral and charged versions. And we also have the phi meson, which is about 1020 MeV per c squared. And also the F0 980 fits in there too, with an energy of 980 MeV per c squared. And the difference between the F0 980 and the phi appears to be a difference in orbital direction. The F0 980 doesn't usually show up in charts of particles fit the quark model because it doesn't fit the quark model. But it can fit the onion theory quite easily. There's also an A0 980 that may have similarly be a kaonium compound, although it could possibly be something else. I'm still investigating that. And so we have a chart of the lower energy kaoniums, and they can be very accurately calculated just by summing up the components. Now in the 70 MeV per c squared resonances, they have a total of 980.36 MeV per c squared added to their total energy. And that's the relativistic mass of two particles that each have 7 electrons or positrons in them, for a total of 14. 14 times 70 is 980.36. So, in order to get the higher energy KK resonance, we add the electron charge for an electron in the middle, then you add the 2 kaons, and then you add the 980, and you get 1968.23 MeV per c squared. And this describes the charged D strange meson, which has a mass of 1968.30 MeV per c squared. And so this illustrates how accurate the model can be, where you can just sum up the masses of particles and get the mass of a newer, heavier particle. Then next we can look at the KDK resonance and sum up the mass of an electron, a KD, kaon, a regular kaon, and the 980.36. And we get 1872.02, and that matches up with the charged D meson, the regular base D meson, which has a mass of 1869.61 MeV per c squared. Then at the lowest energy, we can look at the KDKD resonance and have the mass of an electron, 2 KD resonances, and the 980.36. And we get 1775.81, and that matches the tau meson with a mass of 1776.86 MeV per c squared. And depending on what value you use for the KD, you can get even more accurate estimates. And that brings up the point that the tau really is a meson. It's not a lepton, and it's not an elementary particle. If you actually analyze the decay products, you find that the tau has very complicated decays. It's not simply an excited electron that only decays to a muon or an electron. It has decays to 2 kaons, it has as many as 8, and it has as many as 30 decays total to 2 pions, which are indicative of it being a form of Kaonium. And because of the correct mass fit here, it's obviously a KDKD resonance. And so taus should have always been lumped in with mesons, and they should have been described in any fundamental theory of particles. Then to continue, we can also have the 35 MeV per c squared per particle resonances, which are similar, except we add 490 MeV per c squared at the end, plus the particles like we did in these examples. And that gives us particles like the F1 1285, the F0 1370, and the F0 1500. All these are particles that don't fit the quark theory at all, but they fit the Onium theory quite well. And that's one of the major strengths of the Onium theory, is that all these mid-range, higher energy particles and there are hundreds of them, that don't get explained by the quark theory, can be explained by Onium theory just by looking at the orbital energy and characteristics and the basic composition of the resonances. And there's a couple others that fit there. I'll put a table up with some of the ones from a paper. And I discussed this all in a technical paper that I'll link below. And they're discussed in a book that I wrote called Goodbye Quarks, the Onium Theory, which you can purchase if you want to study it. Or like I said, just read the papers. But if you want to support my research, then buying a book helps me, as does contributing on Patreon if you want. So basically, quarks are just an unnecessary complication. We don't need them. We never needed them. What we needed was a better evaluation of the decay products and relativistic mass energy of the Onium compounds. Anyway, if you like my video, please like, share, or subscribe. Or as I said, you can buy one of my books. I also have 2 books on quantum field theory if you're interested in my quantum field theory research. So thanks for watching.